Okay, so it's first of all, I would say it's a wonderful pleasure to have a chance to visit this place, and also it's a wonderful topic for a conference because of the interrelated sets of ideas and community of people that don't always talk to each other. I'm actually going to talk about a topic. My real topic is about a type of transport anomaly that I'm predicting that is connected with collective behavior in ferromagnets. And but it's this idea is based on things we know about experimental properties of excitonic condensates. So I never know how to give this talk. It's possible to give this talk without ever mentioning excitons, just to the magnetism people, and then there's a notion in magnetism many of you are probably familiar with of spin transfer torques, which is more or less the same thing as Andreev scattering. And but I'm going to give this talk. I'm mostly going to talk about exciton systems, and only at the end I'm going to say, really, I was talking about ferromagnets. Okay, so this is the experiment that I'm going to work towards explaining. It's an experiment on two-layer, two-dimensional electron systems. So the green layer and the orange layer are 2D electron systems. They're actually in an insulating state in this experiment. So there's, and it's in the quantum Hall regime. So these bilayer systems, bilayer electron systems in the quantum Hall regime are the only really clear example of an equilibrium exciton condensate that we know. And so there's lots of interesting experiments that you can do. In particular, in the labs of Jim Eisenstein at Caltech, this data here is from Jim Eisenstein's lab, and from the lab of Klaus von Klitzing in Stuttgart. They've worked quite actively in this area over the last 10 or 15 years. And so first, let me just say for the moment, let me just direct your attention to this red curve. This is, in the quantum Hall regime, as many of you know, the edges, out in this case, in this Corbino geometry, the outside edge and the inside edge are more or less equipotentials. So you should view this as something to do with, let's say, possibility at least of transport from outside, 1D transport from outside to inside. And I'll talk about this later in terms of 1D transport. So in this experiment, the 1D transport from outside to inside is more or less insulating, battery's dying. So what's plotted here. Okay. No, switch.
Just a few seconds to install that.
Sorry about that. I knew I should change the battery. And now I don't know what to do.
Just close it. Just close it.
Okay.
Close this.
Yes. And the pointer is...
The pointer is the red button.
Yeah. Okay, so what's plotted here is the current I2 flowing from top to bottom on the insides as you change the bias voltage from top to bottom. But what the experiment shows is that a current also flows around this loop, even though there's no bias voltage driving this current, and even though the region in between is insulated. So I'll explain why that happens. And also, these, when you plot it, here it's plotted I2 versus I1, but when you plot let's say I1 versus V2, the change in I1 plotted as a function of V2 occurs over, is sharp on the scale of KT. And that's the property that I think is potentially interesting, especially if you could make this kind of thing to occur at room temperature. And it's an example of a collective type of charge transport switching. Our current electronics is based on switching the motion of individual electrons with some gate voltage or something, and that can never be sharper than KT. And that's the fundamental reason that you have to operate electronic devices at a substantial voltage, and they consume a lot of power, and you can't make them any better. In fact, this research is sponsored by the semiconductor industry. And so they're worried enough about the lack of progress that they're supporting lots of research on crazy ideas for what might produce new type of switches, and this is one of them. Okay, metal insulator phase switch devices are another example. Now, I've actually been talking to my magnetism friends about this device for a long, long time, and they used to tell me, that's crazy, we can't do that. But in fact, the type of magnetic system that you need to make a magnetic analog of the exciton system I just showed you, or the bilayer electron system I just showed you, now exists. This is, for example, from a talk by Andy Kent at New York University, and he was working on making this is spin transfer nano oscillator device, but the key capability here is to have nearby magnetic layers, one which is very accurately easy plane, and one which is very accurately easy axis, with a perpendicular axis. And nowadays that's quite routine, although the materials are getting better and better. Okay, so now let me step back and I'll start talking about excitons. As I said, this is going to just turn into magnets at the end. So the notion of exciton condensates, of course, excitons are an electron-hole pair condensate, and there are some qualitative differences between electron-hole pair condensates and electron-electron pair condensates. Traditionally, people look for coherence, macroscopic coherence between conduction and valence bands of a semiconductor, but similar coherence of electron-hole pairs, so you can achieve in charge density waves, spin density waves, or ferromagnetism, as I'll discuss. So it's interesting, these ideas, of course, have been around for a long, long time, and many things have been said about them in the absence of experiments. This is the oldest paper I know, which talks about Bose-Einstein condensations of excitons. And so one of the things that they concluded in the first paragraphs of this paper is that there will be no interesting electrical properties of exciton condensates. And we know now that that's not true. Their argument, of course, was that electron-hole pairs were electrically neutral, so they couldn't carry current. There's another well-known paper by Walter Cohn and David Sherrington, and they said basically that you could never make a superfluid. And although this is sort of correct in a sense, it's irrelevant in practice. Okay. So the system in which, you can use whatever words you like. Exciton condensation. It's entirely equivalent to describe this state as a state in which you establish phase coherence of electrons between two different layers without any electron tunneling between the layers. Spontaneous phase coherence between layers, or in these two-layer systems, sometimes we use a magnetic analogy and call the top layer and the bottom layer a pseudospin, and then it just looks like XY magnetism. Okay? So the system in which spontaneous coherence, maybe that's the most physical language, between electrons in two different layers, between two different groups of electrons, has been observed experimentally, is a two-layer electron system. Fermi levels in the conduction band of a semiconductor, gallium arsenide, usually in both layers. In a magnetic field, in fact, in the strong magnetic field limit. And so, of course, in a magnetic field, the available electronic states are organized into a bunch of energetically separated Landau levels. And the regime, the state is, one way to describe the state is to look at the lowest Landau level of two layers. When those Landau levels are partially filled, if you like, you can make a particle-hole transformation one of the layers. And this exciton condensate state occurs when the number of electrons in the lowest Landau level of one layer is equal to the number of holes in the lowest Landau level of the other layer. And so it turns out when you add the two layers together, you have enough electrons to fill one Landau level between the two layers, or total filling factor 1. So I'm going to come back in just a second and try to explain what's going on in those transport experiments I showed you. And the key idea is very closely analogous to Andreev scattering in a superconductor. Here's a bag cartoon of a circuit containing a superconducting element, normal metal elements and superconductors. Of course, superconductors have an energy gap, and you might think initially that a quasi-particle from a normal metal at the Fermi level wouldn't be able to get into a superconductor. And of course that's true if the temperature is low enough. But because of the broken time reversal broken particle number symmetry of a superconductor, a normal metal quasi-particle can be Andreev scattered as a whole. And so that means it's actually this quasi-particle process violates particle number conservation. And the way that on-physical thing is cured is that a Cooper pair is launched to conserve current. And when you describe this in a mean field language, that means that the transport steady state is one in which the superconducting pair has a gradient of its phase inside the superconductor so that a current flows through the superconductor and the current is constant everywhere in this wire. Okay, so similarly in these bilayer exciton condensates, so this is labeled here top and bottom for the two layers, left and right, but this is actually left and right is really outside to inside of a Corbino ring. And in that experiment, it turns out in these quantum Hall systems you can adjust the degree to which particle numbers are conserved separately in the two layers. In other words, you can adjust the degree of either coherent or incoherent tunneling between the two layers occurs. And in that experiment, the first experiment I showed you, the tunneling is turned off. So particle number is conserved separately in the top layer and the bottom layer. Nevertheless, when you form a exciton condensate, when you have an electron-hole condensate amplitude, then just like the pair creation terms in the mean field theory of a superconductor, the electron-electron interaction then the quasi-particles can scatter off the condensate, and that interaction introduces a large amplitude for the quasi-particles of the system for tunneling between top layer and bottom layer. So the quasi-particles, the mean field Hamiltonian and the quasi-particles in the broken symmetry state don't conserve particle number. And this quasi-particles come in, they see a gap, just like in a superconductor, so they can't get into the bulk of the region between the outside and inside of the Corbino ring. They see a large amplitude for tunneling from top to bottom, and so they can have a certain probability of tunneling from top to bottom, and whenever that happens, a exciton is launched to conserve current separately in the two layers. Okay? So, for example, in this experiment, this is an experiment that observes this phenomenon most directly. So here's the two layers again. Here, bias voltage tries to drive current in the top layer from the outside to the inside. And if there's no wire connecting outside and inside on the bottom, then in fact hardly any current flows. Okay, there's a little bit of current that can flow over the gap, but basically no current flows. There's a huge resistance. If you do have a resistor connecting top and bottom on the bottom layer, then what happens is there's a path for the quasi-particles to get from one side of the battery to another. They tunnel from top to bottom, then they go outside of the system, then they tunnel from bottom to top, and then they can close this loop. So the end result is that even though there's absolutely no tunneling in this experiment, you have to trust me, for electrons to get from top layer to bottom layer, when you put a bias voltage in the top layer, a currents flow, which you can measure externally through top layer and bottom layer. They flow in opposite directions, and these currents through these loops are being completed by a flow of a super flow, as far as one can tell, of electron-hole pairs across the Corbino ring. Now, the next, so that's one of the important type of transport anomalies that occur in these exciton condensates. The next one is related actually to the type of physics that Cohn and Sherrington were referring to. In these exciton condensate systems, you can actually turn on the tunneling from top layer to bottom layer. And when you do that, you can derive a equation for this. So this is actually done in the kind of magnetism language. This is kind of a current conservation equation. And what it says here, this is the gradient, or the divergence of the gradient of the phase. So this is like the divergence of the supercurrent, accumulating charge in one layer or the other. And this is a tunneling amplitude. So if you have collective coherence between the two layers and you have some tunneling amplitude between the layers everywhere in the system, then these pseudospins, if you use that language, can persist in this effective magnetic field. And so this looks obviously a little bit like Josephson junction, and you can make an analogy to that too. So that's another type of way for charge to flow from the top layer to bottom layer. And this is what the quasi-particles are doing. This illustration from this paper several years ago uses the language of magnetism to describe the statement that whenever quasi-particles go from one layer to another, you have to launch a Cooper current. So that's why this says torque here. This is a spin transfer torque, or a pseudospin transfer torque in the magnetic language. And this is because the quasi-particles are violating separate conservation number in the two layers. And as long as this current is the quasi-particle current flowing through the system is not too large, you can satisfy this equation, and lots of quasi-particle current can flow. And you can integrate this equation over the system, and then you get it. Whoops, maybe it's in the. You can write it in. If you integrate this over the 2D system, all of this says is that there's a contribution. That the net current over the entire system flowing from top to bottom has to be, so that's, that charge being injected to one layer or the other in the steady state has to be sunk by this coherent tunneling between the two layers. Okay, so, this is another transport measurement. What this is a bilayer system, both layers. The red curve is both layers contacted in the normal way, nothing strange happens. To see all of these effects associated with interlayer coherence, you have to always make separate contact to the two layers. And so this is an experiment where you have a current source in the top layer and a current drain in the bottom layer. And the IV curve, you can see there's two different regimes. It goes from a low resistance state to a high resistance state. This is actually the same data, but with the voltage measured just between top layer and the bottom layer. In the system, this voltage actually includes a contact resistance. And what this experiment shows as far as the 2D system is concerned is that if I have tunneling between the layers, if I try to do a tunneling experiment, if I try to make current flow from top layer to bottom layer, a certain amount of current can flow without any voltage between top layer and bottom layer. It's like the two layers are completely coherent. They're just one system, so how could there be a voltage? And then, but there's a finite amount of current that can be sunk by this interlayer tunneling. And so once you put too much current in, then the phase coherence becomes time dependent, and you go into a different regime, which is described by this equation. Okay. So this is kind of the pseudo-spin language. These two equations are more or less the same. The one on the bottom is the integral over two-dimensional space of the one on the top, basically. And this is the rate at which the charge difference between one layer and the other layer is building up in the 2D system. And so in the steady state, this has to be 0, like it is above. And there's a part that comes from the interlayer tunneling amplitude. And there's a part that comes from the quasi-particle currents that are flowing from top layer to bottom layer. But what happens when, so there's one steady state that I've been talking about so far mainly, where the order parameter of the system is time independent. So this is the interlayer phase angle. We have spontaneous coherence with a phase. This is its time dependent. So what I've been talking about so far is no time dependence. And so what happens when you have time dependence is that this interlayer phase angle becomes time dependent, and then there's two things that happen. So now there is a time dependent voltage between the layers, which can drive incoherent tunneling, like in normal tunneling spectroscopy between the layers. And this is that interlayer tunneling in ohmic approximation. And the other thing is you have to correct the quasi-particle current flow for the fact that the order is time independent, and it turns out you can get rid of this time dependence of the interlayer phase just by gauge transformation, as people often do in theories of superconductivity. The effective bias voltage between the two layers is reduced by this time-dependent phase. So there are two regimes that you can see in this experiment. One is, or in the experiment I just showed you, one is a regime where phi dot is 0, and a certain current flows between the layers just determined by the properties of the contacts, which control this quasi-particle conductance. This is a little g here is just conductance in some convenient units. And then then this term balances this term. This is what people call spin transfer torques in ferromagnets. And then there's a regime where the interlayer phase is time dependent, and then this term, because phi starts to increase with time, the average of this term is essentially 0, and the quasi-particle current that flows into the system is reduced for a given bias voltage, let's say, and it's sunk instead by incoherent tunneling between the two layers. Okay? And so that's what you see. This is the regime with two layers are essentially one system, and but if you put in too much current, then you go into a regime which is kind of like normal tunneling between two different layers. And so that's seen experimentally. And the interesting, it's interesting to use those same ideas. I won't try and take you through the algebra, but you can use those same ideas, all the same ingredients, but say I have two contacts, for example, at the inside and outside of a Corbino ring, or at one place and another in a ferromagnet. And it turns out that current, you can derive equations for how much current flows at left and right, and that's what this experiment is showing. Okay, so let me try and give you the qualitative ideas here. So the red curve is, so we have these connections. What's being varied here is V2, the bias voltage on the inside of the Corbino ring. And what's being plotted on the vertical axis is the bias voltage, or the current flowing, quasi-particle current flowing to complete this current on the inside of the Corbino ring. And you can see that there's no voltage, or nothing happens out at the other side of the system, at least. What's plotted along this axis, it's just off your screen for some reason, is the current flowing on the outside of the Corbino ring. So since this is an insulator and there's a current flowing on the outside, current flowing on the inside being driven by a bias voltage, why should anything happen on the outside? And nothing does happen until the order parameter becomes time dependent. And then the order parameter suppresses the amount of current that flows from top to bottom on the inside, and there's actually a current. If you see this, what happens is that I2 is positive and I1 is negative, or in the other branch, the two currents flowing in inside and outside have the opposite sign. The blue curve and the black curve are the same plots of I2 versus I1, both parametrically depending on V2, at a fixed value of V1 that's not 0. And involves the same physics, and the important thing from a device point of view is you can change the IV curve at the outside very quickly if you're close to these boundaries by putting a small bias voltage on the other side. Okay. Okay. So now I have 3 minutes. Okay. So I hope you got the rough idea. I'd be very happy to discuss all those ideas with people in detail. Be nice if we had this at room temperature. In the quantum Hall bilayer exciton condensates, this stuff doesn't occur above 100 millikelvin, or below 5 Tesla magnetic field, so it's not very useful. Graphene is attractive in many ways, as Alex was explaining. I think that Leonid's experiments kind of are pretty convincingly show that the electron-electron interactions in graphene are not strong enough for this effect to occur. And so maybe bilayer graphene will get you there. Transition metal dichalcogenides are attractive. They're also two-dimensional material. They have a lot of the same advantages as graphene. But the point I'm trying to make with this picture is that the problem of graphene is very different from the normal BEC BCS crossover problem, because when you go to low density, if you don't have a gap in each layer, so this is a system with a low density of holes, let's say in the blue layer, and low density of conduction band electrons, of holes in the red layer and conduction band electrons in the blue layer. And because there's an energy gap in the two-dimensional semiconductors on both sides, you can forget about these remote bands. And I think it's really these remote bands that are killing the possibility of forming this state in graphene. And these transition metal dichalcogenides, in the BEC BCS crossover problem, the maximum TC you can get scales with the exciton binding energy. And the exciton binding energy in these transition metal dichalcogenide two-dimensional semiconductor layers is somewhere between 0.5 volt and 1 volt. So you have a big starting energy scale to work with. So as Alex was saying, the materials are nowhere near good enough at the moment, but maybe you can get there. Okay, so how about then doing it with magnets? We know there are lots of magnetic systems that are ordered at room temperature, and in order to have my bilayer system, I was injecting electrons. I can make contacts. All of this physics depends on making contacts that are contacts to the top layer or the bottom layer. We have a state which is coherence established spontaneously between top layer and bottom layer. If I have an XY magnet, I can view an XY magnet as being a coherent combination of spin up and spin down, okay? With the phase difference between spin up and spin down being equal to the azimuthal orientation of the magnetization. And so I need XY magnets. I need to be able to inject into XY magnet spins that are up and down. And nowadays, it seems like we really have the materials we need to do this. This is a talk that Andy has given about state-of-the-art devices which are trying to realize an idea they have for making an oscillator out of somewhat related things. And the magnetism community would describe this as spin transfer. You can translate that to Andreev scattering. But this is just with a single device and with the same materials. Just simple materials that people have a lot of experience with. If you have a sheet of permalloy, a nice XY magnet, and you have low resistance spin injectors that you can place in different places on the spin, on the permalloy nanomagnet, thin film nanomagnet, then I think we can see all of those transport properties that are being seen now at 100 millikelvin in quantum Hall systems, that we'd be able to see them at room temperature. And maybe people will be able to figure out how to make a useful device out of it. Okay, so I stop there, and thank you for your patience.
Right, we don't have too much time for many questions, but maybe one or two short, and then otherwise coffee will get cold. No.
What you're measuring with this geometry, the two Corbino disks on top of each other, is it analogous of the Josephson?
It's
of the DC Josephson effect.
There are analogies with Josephson junctions. The analogies with Josephson junctions become sharper if you think of systems where you have some big magnet with more or less thin phase, and then you put a bunch of little smaller superconductors with more floppy phases. Then the analogy with superconductor becomes closer. So certainly a lot of the ideas involved in non-equilibrium superconductivity are very relevant to the phenomena that occurs in this system. These ideas have been, in this case, explored much less extensively than in superconductors. And I hope, as I was saying, that that we'll have similar class of phenomena to explore in magnetic systems.
Are these systems stable at very high voltage?
In the quantum Hall case, or what?
In your Corbino rings?
Or in these, what is the voltage scale that they?
If you draw the large voltage.
Yeah, so it depends on the contact resistances and stuff, but the critical currents usually correspond to bias voltages in the microvolt regime. And so when I claimed before that you can get switching that's sharp on the KT scale, I'm talking about a big change in current flowing in external circuits at 100 millikelvin for changes in voltage that are sub-microvolt. So we want to change all of those things, but if this kind of magnetic device I'm talking about works, then the whole way it will change the power consumption problem is that the operating voltage will be millivolts instead of volts.
Okay, that's something very short.
In the bilayer electron system, when it forms the Josephson phase, does it essentially mean there's a massive dipole moment? When you have to,
Interlayer tunneling.
Yeah.
There is a energy cost for moving charge from one layer, or at least there's the energy charge for moving from one layer to another. That curve has a second. So it means that there's a preferred value for the interlayer phase. So when you look at the dependence of the energy on the interlayer phase, there's a contribution even at zero wave vector. And that sometimes people refer to that as a mass. Maybe that's what you have in mind. Okay, so
I'm
we'll
afraid I
discuss
have to
it.
continue discussing during the coffee break.
Thank you.
So thanks again to the speaker. And the next presentation will be given by Marco Polino.